before we start this lesson, let's recap what we've learned thus far. We've covered that the instantaneous rate of change is the same as the slope of the tangent line at a given point, which is the same as the derivative at a point, and which we represent with f prime, or dy dx, or d dx, just depending. How we began this unit was looking just at average rate of change, which sometimes is referred to as estimated rate of change, which is just the traditional concept of slope. So up to this point, we've kind of been looking at both of these forms. But from this point forward, it's kind of funny because this video is on motion. Anytime you see the phrase rate of change, we're always going to assume that it means instantaneous. So what that means is you don't need to ever assume it means average rate of change. If a problem wants the average rate of change, it has to actually put this word or this word in front of that phrase. So the other concept we've kind of covered recently is that if f of x represents any type of quantity, whether that be distance, population, amount of snow fallen, number of days we missed school, I'm getting a little ahead of myself here. If that just represents the quantity itself of whatever we may be talking about, then f prime of x, again, we're always assuming instantaneous rate of change from this point forward. This derivative value, or function, is going to represent how the quantity is changing. So the most probably famous way that we think of this in context is where our quantity represents a position, and how that position is changing can be described as the velocity. And then if we take it a step further, if our quantity is the velocity, then how the velocity is changing can be described as the acceleration. And this concept of motion is one of the reasons we ended up with the idea of the derivative to begin with, thanks to Isaac Newton, who at the time was working a lot with gravity and other forms of motion. Okay, so let's get to some notes here. So how can we describe motion through the use of functions and their derivatives? So let's start with the concept of the position of an object. So in a lot of the word problems you'll come across in AP Calculus, the position function will be denoted with s of t. And there's kind of two different questions you can ask for the specific position at a given time, obviously, which would just be the y value when you plug in to the function s of t. However, the other thing that you may be asked about is the overall displacement of an object, which is simply the amount of change in a position on a given interval. So let's write the more formal way of saying that. So given a position function s of t on an interval ab, the amount of displacement will be calculated as s of a minus s of b. So you're just finding the amount of change that's occurred on that given interval from the beginning to the end. Except Miss Wright wrote these letters in the wrong place, so let's fix that. So s of b minus s of a. That's right. So normally when we look at the change in something, we take where it ended and subtract where it started. That makes a little more sense. So the other thing you can be asked about in regards to position is the total distance covered that an object covers. Okay, so what's the difference between that and displacement? Well, displacement I kind of think about as like if I look at the beginning of my day, I'm at home, then I drive to work. So that displacement would just be the amount of difference in position those two things are. But the amount of distance I've covered driving to work can be very different, right? Maybe I went to get coffee and then I had to go over here to a gas station and then I had to go along all this other stuff, do all these errands, and then I ended up at school. So the displacement would be the same no matter what I did on my commute. However, the total distance can vary greatly. So this might seem redundant, but it's basically the total change in position. Alright, so up next we have velocity. So velocity describes how our positioning is changing, and because of that it's represented with a derivative. We typically use v for velocity, and then it's simply equal to the first derivative of our position function. It describes not only how fast something is moving, but also it gives us a sense of direction. Okay, and so typically when we talk about how fast something's going, we like to use the word speed. However, the speed of an object can't be negative, whereas velocity can. So for example, if the velocity is positive, that means we may be going to the right if we're going left and right. Negative would mean we're moving to the left. It could also mean going up and down. It just depends on the scenario. But the speed must always be positive. So the way we represent that is the absolute value of the velocity, or the absolute value of that first derivative of the position function. Okay, and if you want to make a note, because of that absolute value, that means our speed must always be a positive value. So speed doesn't tell us direction, but velocity does. So velocity tells us how the position is changing, how something's moving. Up next is acceleration, which is another layer down, and it describes how the velocity is moving or changing. Okay, so the acceleration was denoted with an A for acceleration, and it describes how the velocity is changing. Therefore, it's the first derivative of the velocity function. And that means it's the second derivative of the position function. It tells us how velocity is changing. So for instance, your speedometer tells you how fast you're moving at a specific instant, so the velocity, but what you're doing with the gas pedal is determining what happens in that next instant, and that's how we kind of think of acceleration. It's how that velocity or speedometer will start changing. So it helps me to think about the fact that if acceleration is positive, then velocity is increasing. And of course, the other scenario, if it's negative, velocity is decreasing. Now that doesn't mean it's just decreasing to 0 and then stops. It might mean our velocity is getting more and more negative, which can still be a way of speeding up. We'll get to that in a minute. Okay, so a lot of the examples we do with these problems are quadratic functions, which you should be very familiar with. And I think you guys will be fine with those. But I do want to take some time to look at the ones that are less familiar, which deal with rectilinear motion. What does that even mean? Well, it has the root word kind of dealing with the same thing as a rectangle. And it simply means an object that travels in a line. Okay, and just like the sides of a little rectangle here, sometimes the sides move left to right, which at times you might hear them describe as moving along the x-axis, similar to a rectangular coordinate plane. And the other parts of a rectangle move up and down, which, if we think of a rectangular coordinate plane, would be going along the y-axis. You know, we can put an and here. It bothers me that they're not the same. Okay, so it can move left and right, or it can move up and down. And they usually give you that information in the problem. That way, if the velocity is negative or positive, you know what orientation that would be. Okay, so often this is used whenever we're talking about a generic particle in motion. So let's do an example. So we're going to let the function s of t equals t cubed minus 12t squared plus 36t minus 20. Describe the motion of some particle we're going to call p as it's moving along the x-axis, so we're thinking of left and right in this problem, as it's moving on the interval -1, 9. So I know that our domain here represents t as in time, and normally we say no negative time. However, in these more generic problems that don't have a ton of context, it would simply mean before the start, technically, so right before time 0 and then after. If you're working with some sort of quadratic in context, it's still usually the case that we don't think of the negative times as solutions. But in this case, they're giving us the domain, so we're going to work from -1 to 9. So we could ask ourselves, what is the position of the particle at 0? And so this would be a very straightforward question, one where you would simply just use the position function given and evaluate it at 0. And if we did that, all these terms with t's would simply go to 0, and it would leave us with -20. Okay, and the units would literally be units, because we're thinking of like a coordinate plane here, so it's nothing fancy. So that would be all you would need to do to answer any question on position. So our next question will be, when is the particle stopped? So that's a way of asking us, when is the velocity 0? It could also kind of be the same question of where is it changing direction? Right, so if a particle is at a speed of 0, that means it's stopped, and it also means it could be passing from a negative velocity to a positive velocity, and thus crossing through a velocity of 0 in between. So all of those questions would really be asking about the same thing. The easiest way for most of us to think about it is just its meaning to find the velocity function and set it equal to 0. And if we remember, the velocity function is equal to the first derivative of the position function. So in this case, let's take a look. That's going to give us 3t squared minus 24t plus 36, just using our power rules. So now we're setting that velocity equal to 0 to find out when the particle is not in motion. And there's lots of ways we can solve quadratics. Obviously, if you can factor it, go for it. A lot of times they'll be nice and give you a GCF that makes it a little bit easier to do without a calculator, which is the case here. So that would give me t squared minus 8t plus 12. If it was not factorable, of course, you could still use the quadratic formula. That's always a great approach. If you have a calculator, you could try to find the roots. It's all up to you. Okay, so in this case I factor it, and I get that the particle is not in motion, or is stopped, at a time of 2 and 6. And I meant to mention earlier in the problem our time will be in seconds. That's kind of important. Okay, so those are our the times. Now a follow-up question we could ask is, when is the particle moving left or right? And even if it just asks you this second question, you would still need to do this step to find those places where it's changing direction. So we're going to use that and kind of make a number line. And we're going to be using number lines a lot in this whole unit, so get used to it. So I'm going to use a 2 and a 6. That's where it's changing. And what we're going to do here is we're going to use this kind of factored form to substitute in some practice values here. Okay, so we know that the particle is not moving at 2 and 6, so we will not include those in our intervals. They'll be open at 2 and 6. And then I'm going to kind of actually erase these arrows. So we're doing a number line, but we have a closed interval for this problem. The smallest it could be was -1. So I'll put a closed dot there. The largest it could be was a time of 9. So that helps me not forget that. So no negative infinity, positive infinities here. It's a closed interval. Okay, so these numbers on the bottom are just our t's, as in times, seconds. And what we're going to put on along the top of the number line, we're going to put pluses and minuses, and that'll represent our velocities on those intervals. So what we're going to do is use this function to kind of do substitute values in. So a number between -1 and 2, you can pick any number. 0 would be the easy one to try. And if I plugged it in, well, 3 is always going to be positive in each of these intervals, so I'm just going to leave him out front. Then we have 2 parentheses where we're plugging stuff in. So I'm going to go ahead and set this up all the way down. Okay. So if I came up here and I plugged in a 0 for t, right, 0 minus 6, that gives me a negative number. If I plug it into the other factor, 0 minus 2 also gives me a negative number. A positive times a negative overall means that the velocity is positive from -1 to 2. Then we're going to do it for 2 to 6. So maybe pick a 5, a 3, a 4, doesn't matter. It's just a test point. So if I were to plug a 5 into this first interval, that would give me a negative number. If I plugged it into the second one, however, that would give me a positive. So now I have 2 positives and a negative. So overall, the velocity in this middle section is negative, or moving left. Okay, then we come to the last one, something between 6 and 9. I'll go with 7. Doesn't really matter. 7 minus 6 is positive, and 7 minus 2 is positive. So everything's positive in this last one, which means that the velocity is positive in that interval. So we can say with confidence that our particle is moving left in this middle section here, where the velocity was negative, and those would both have open intervals. So from 2 to 6, it's moving to the left, and it's moving to the right here. So this is including the -1 that was closed, but the 2 is not. So we'll say it's moving to the right from -1 to 2, and also from open interval 6 to closed interval 9. Easy peasy. Okay, so now we know where it's not moving, where it's moving left, and where it's moving right. So for our next question, we're going to ask, when is the particle not changing speed? And this is kind of the same as asking, when is the speed constant? And both of these we're going to think of as, where is the acceleration 0? Okay, and so as we remember, the acceleration is describing how the velocity is changing, which means it's the derivative of the velocity, and that makes it the second derivative of the position function. So just as a quick reminder of what our velocity function was, and now we will take the derivative of that to get the acceleration. So that becomes 6t minus 24. And we want to know when that acceleration is 0, or the speed is constant. It's not increasing velocity or decreasing velocity. And this one's pretty easy to solve. I still prefer to factor with each of these, just as good practice, but you could move the 24 over, obviously, and go from there. Okay, and so we're getting a time of 4 seconds as whenever the particle is not changing speed. So our follow-up question here will be, when is the velocity increasing and when is it decreasing? So please understand that's different than asking where it's positive and negative, right? We're describing how it's changing when we say the words increasing and decreasing. Okay, it doesn't mean anything about whether it's positive or negative, it just means it's getting more positive or getting more negative. So we're going to make our number line again, putting our -1 and our 9, and this time there's only one value where anything's happening, which is at 4. And this is why I like to use the factored form, because it helps me with the number line tests. Okay, so again, the bottom here is our t, and then this will represent the sign of our acceleration. So I'm really just using 6 times t minus 4, so a positive number times a factor. So let's say for the first one, we're going to do, what's something, oh, 0. Always love 0. So if I come up here and plug a 0 in, that's going to be 0 minus 4, which gives me a positive times a negative, which means overall the acceleration is negative from -1 to 4. And then if I come over here, let's say I pick a 5, plug that in, that's going to give me a positive. So the acceleration is positive from 4 to 9. So now we're going to be able to state that the velocity is increasing from 4 to 9, and I forgot to put that. You can't include 4 here, because again, that's where the acceleration is 0. So it's not increasing or decreasing there. So from 4 to 9, 9 is inclusive. And then velocity is decreasing on the lower half from -1 to 4. Okay. I like to avoid using the words accelerating and decelerating because we have certain connotations with that. And it actually leads us to what's next, which is how do we describe where a particle is speeding up and slowing down? The acceleration alone doesn't tell us that. So this is the question we really like to ask. So for this last one, we'll ask, when is the particle speeding up and when is the particle slowing down? So in order to ask this question, we're going to combine our velocity and acceleration number lines. Okay, so let's make one really big number line here. We're just combining their signs. So we know -1 was the start and 9 was the end for both. But let's take a look back. So for our velocity ones, we were looking at the numbers 2 and 6. And for our acceleration one, we were looking at 4. So we need to put all 3 of those on our number line. So 2, 4, and 6. Okay? And remember, it can't be doing any speeding up or slowing down at each of those. Alright, so now we're going to put I'm going to put our velocity signs on the top and our acceleration signs on the bottom. You obviously can do it whichever way, it doesn't matter. Okay, but let's go back and look at velocity. So the velocity was positive from -1 to 2. So it was positive here. Okay, then it was negative from 2 all the way to 6. So it's negative here, and it's still negative here. And then for the last one, it was positive from 6 to 9. Okay. For acceleration, it was negative all the way from -1 to 4. So here and here. And then everywhere after 4, it was positive. Positive, positive. So what causes a particle's motion to speed up is whenever the acceleration and velocity are doing the same thing. So there's 2 places here where our particle will be speeding up. It will be speeding up right here and right here. So you'll notice it doesn't matter which direction it's moving in. If the acceleration is also moving in the same way, that's what causes it to speed up. So we're always looking for their signs to be the same. And for this particular problem, speeding up will be occurring from 2 to 4 and from 6 to 9. So of course, slowing down is whenever they're different signs. It doesn't matter which is which, but anytime they're not the same sign for velocity and acceleration, that's what's causing it to slow down. Okay, so for this problem, that'll be from -1 to 2 and from 4 to 6. Ooh, that's a 6. Awesome. So we'll continue this particular example tomorrow in class. I'll ask you some questions about finding the total distance and the displacement and maybe the speed at a certain time. But this will conclude our video part of this example on velocity, acceleration, and other rates of change.